All right, let's get started with this session. So I'll be chairing the session, and it has two talks in the session now. And the first talk is by Professor Jeroen van den Brink from the Leibniz Institute in Dresden, and he's going to tell us about topological surface superconductivity in this platinum bismuth. So we'll have the talk, and then we'll have a round of questions before we move on to the next.
Okay, thank you, Arun. I'll talk about this material, platinum bismuth 2, and I'm a theorist. Actually, I used DFT quite a lot, or in our group, in our institute, we use density functional methods quite a lot. But today, it's a talk that's more experimental than theoretical, which means that I'm a bit out of my own turf. I hope you won't mind. Actually, by show of hands, who of you is an experimentalist? And theorists? Okay, about 50-50, so that's good to know. The special thing is that the words connected to this material are topological. There are topological surface states, and those topological surface states are superconducting. This work's done in Dresden by the theorists there, which are my institute, and experimentalists there that are at the institute led by Bernd Büchner. Okay. So let's get into platinum bismuth 2. It's a two-dimensional, quasi-two-dimensional system, or it's a van der Waals system. It's a stack of layers. It has this P31M symmetry. It's in the center platinum on top, and below this single layer there's bismuth. And on top it looks a bit different than on the bottom. So the orange one we call kagome-like, and the green one, just to give it a name, we denote as a decorated honeycomb-like. As I said, it's a quasi-2D material. The interaction between the layers is there, but it's not very strong. And it has a broken inversion symmetry. Other symmetries that it has is time reversal, so it's non-magnetic. And it has 3 mirror symmetries. I'll show them later to you. Maybe you start the time, or somebody starts the time. Yeah, so that I know where I am. Okay. And spin-orbit coupling is relevant in this system. So the interesting topological features come from a Weyl point. So this is the Brillouin zone. This is the band structure. This spaghetti are the bands. And the interesting point, the Weyl point, here plotted between the gamma point and the M point. The gamma is the center of the Brillouin zone. M is at the edge of the Brillouin zone. So just to just to help myself. Okay. So what is a Weyl? What's a Weyl point, and why is it topological? So certainly you have heard about Dirac points. Graphene has the famous two-dimensional Dirac point, but there are also systems with a three-dimensional Dirac point. And Dirac point is twofold degenerate, the bands. Now, if you break inversion symmetry, and you do that in presence, for instance, in the presence of spin-orbit coupling, you split up the Dirac point into 2 separate points. So now you have non-degenerate crossing points here that are described by a very simple low-energy Hamiltonian around this point. The Hamiltonian is H is equal to plus or minus K dot sigma. K is the three-dimensional momentum, and sigma is the three Pauli matrices. Yeah? And the one of the Weyl nodes has a plus sign, which is the chirality of the node, and the other node has a minus chirality, and the total chirality of the 2 nodes together is 0. They are born out of 0 and get a chirality plus or minus 1. And this is a very stable situation. And this goes already into the direction of topology, because now you can think to add a perturbation to this Hamiltonian. So you have this very simple Hamiltonian, these 2 points, add a perturbation. Well, let's add a perturbation with the parameter Q, and now we have to add a Pauli matrix there, some type, Sx, sigma x, sigma y, sigma z, or sigma 0, whatever you want. That is the form of this perturbation. And you see that I can absorb this perturbation into a new Hamiltonian, k prime dot sigma. Yeah. So what any perturbation does to a Weyl, if it's not a huge, great perturbation that moves around this structure of these nodes, but what any perturbation does to the Weyl nodes is either shift them in energy or in momentum space. But the node stays there unless two monodes coincide, come together, they annihilate each other, they form a Dirac cone, and for instance, a Dirac cone can gap out by a further perturbation. Okay, another way to see why a Weyl node is topological is to go to the Chern insulators. I just repeat something about two-dimensional insulators, Chern insulators that are also sometimes called quantum anomalous Hall insulators. So if you have a system that has a Berry curvature and you integrate the Berry curvature over the Brillouin zone and the system is gapped, then this integral of the Berry curvature of the Brillouin zone is guaranteed to be 2 pi times a integer, and this integer is the Chern number. If I have a quantum anomalous Hall insulator, this anomalous Hall conductivity, for instance, the integer Hall effect is such a situation. If I have is also such a situation, I have a quantized conductivity E squared over H times my Chern number. And this conductivity in a system that is insulating does not come from the bulk. There's the gap, but it comes from the sides because you have a topological edge state sitting there that connects the valence and conduction band. So here you have your insulator and you have a edge state that basically goes around here. And this is a situation where time reversal is broken. To change the Chern number of this band complex, you have to close the band gap here and reopen it again. You have to do something violent or something that really change your band structure fundamentally. So that is also another way to understand topology, that the system is relatively robust against external perturbations. So the Chern number is conserved as long as these band gaps are not closed. Okay, so now how does this translate into the physics of a Weyl semimetal? Weyl nodes actually separate Chern insulating planes in momentum space. Yeah. So what I can do is fix one K component. So I'm in three-dimensional momentum space, I fix one component, one momentum. Then I have two other momenta. So I have a plane. And of a plane, I can calculate a Chern number. I have a two-dimensional band structure. I have an energy as function of kx and ky, I say. And there will be bands, there will be gaps. And at each gap that I have, I can ask, okay, is there a Chern number related to this gap? Is this a trivial gap or is this a non-trivial gap? So here is, for instance, a chunk of, so these planes are here in light blue. There's a chunk of planes here between these two guys where I have a Chern number 1. And here, planes that are cut like this, they make up band complexes that have a Chern number 0. So I have in momentum space, I have a trivial insulating region, Chern number 0, and I have a Chern insulating phase, Chern number 1. And when you go from 1 to 0, the gap has to close, the gap that makes up this insulating states. And if it closes, there actually you find the Weyl node. You also see that there should be edge states related to this Chern insulator, and there are. And these insulator, these one-dimensional topological edge states for the Weyl semi-metal are called Fermi arcs. They live only in a portion of the Brillouin zone, only in the portion of the Brillouin zone that carries this non-trivial Chern number. Okay, so another way of looking at it, the Fermi arcs and the Weyl semi-metal. Here I have these two Weyl nodes. They carry opposite chirality. They are related by a Fermi arc. For instance, this one is in Chern, this region Chern number 0, this region Chern number 1. The arcs connect the projected Weyl points of opposite chirality. They are edge states, they are surface states, connecting the Weyl points of opposite chirality as their momentum are projected on the surface that you are considering. Another way of looking at it, the Fermi arc is where the Fermi level cuts to the dispersive plane in the Brillouin zone. Yeah? So there is not a single line, there is really a plane of states. So now this is energy, this is momentum. In the Brillouin zone, there's a plane connecting the cones. So whatever I do with my Fermi level, if I shift it up or down, I'm always confronted, I always have these Fermi arcs. They can grow in size or they can shrink in size, but as long as these, say, cones don't start overlapping, there is a remnant of the Fermi arcs at the Brillouin zone. Now let's look at platinum bismuth 2. Do we find it there? Yes, we do. As I told you, there is a Weyl point there between this gamma and M point in the Brillouin zone. These are the iso energy contours. So if it really looks like a cone, it's slightly distorted, but not very much. And this is a Weyl node, as we call it, of type 1. Of type 2, that would be another part of the cone that would go through 0. Okay. Actually, if you do a DFT calculation, you can calculate how you can search for Weyl nodes, and you can find Weyl nodes 48 millielectronvolt above the Fermi level. And the Fermi sheets are really complicated objects, but these nodes are supposed to be here in green and red, probably very difficult to see. So now I have a Weyl node, and I can ask, what is the spin texture around a Weyl node? So in that sense, maybe you're thinking about edge states of topological insulators, and in topological insulators you have a Dirac cone that forms, and the Dirac cone is special because there is spin momentum locking. The spin of the electron is related to the momentum of the electron on the cone. That's not true for a Weyl node. The spin texture can be anything. It's something that is not governed by the topology of that node. This is how we found, if you make a sphere around this node here, you find that the spins point in some kind of direction. But there is a spin-orbit coupling, so there's only one sheet of energies with this spin texture. There will be other sheets with other spin textures. So I'm in the Brillouin zone. I have a 3-fold symmetry, and actually I have 12 Weyl points. So actually, if I start with one Weyl point at this 48 millielectronvolt with a certain chirality, I already know there has to be the other one with another chirality. And then I apply my symmetry operations, my mirrors, and my time reversal symmetry, and in total I get to 12 Weyl points, which are all generated from a single one that I started with. Now, just for fun, let's look how symmetry relates Weyl points. So this is my mirror line. I start, for instance, I can start with Weyl point that I numbered. I give the number 4 here, and it has a chirality blue, let's say plus. And the spin that's pointing in this direction, left upper corner. if I do a mirror, well, my spin in the z direction changes direction on the mirror. The spin that is direction pointing perpendicular to the mirror plane does not change direction, so my spin from left up pointing goes to left down pointing. And under the mirror, the left-handedness or the left chiral, or the plus chiral, I called it, the blue node is mirrored into the red node. Now I can do time reversal. If I have time reversal and I start with the red node, well, time reversal, what does it do to spin? It, of course, flips the spin, and it flips momentum. So here I go from time reversal from 1 to 3. The spin indeed is flipped, but the time reversal does not change the chirality of the nodes. So in that way, you can, by all these symmetry operations, find all the nodes and find all the spin textures around those nodes of certain chirality. Okay. Now, as to the system again, platinum bismuth 2, there are 6 arcs on each, Fermi arcs on each surface. So that is surface K, which are kagome-like and decorated honeycomb. They have very different structures, so their arcs, their Fermi arcs, will be slightly different. They will always connect those two Weyl points of opposite chirality, but they are different. And in particular, it is not guaranteed that a Fermi arc does not lies in a gap of the bulk band structure. It can lie in a part of the bulk band structure that is occupied. And this is here in gray, and you see that for this termination, which is the decorated honeycomb, a part of the arc actually does not overlap with the bulk band structure. So it's really pristine and distinct there, separated from anything. Well, there's nothing in the bulk, so it's separated from it. Okay, the Fermi arcs of this DH, you can calculate also how far they penetrate into the bulk. So this is the wave function squared, and this is the depth into the system. The Fermi arcs are on this line here, and you see the dark one is on this high symmetry line, on the gamma M line, and that one is most centered on the surface. And if you go away from that one that is most centered on the surface, go to the yellow ones that are closer to the Weyl point, you see this, for instance, this yellow one, it starts to be stretched out more and more into the bulk. Where actually, if you would be able to go all the way to the Weyl node, the Fermi arc would actually disappear completely into the bulk. It would delocalize into the bulk. Yeah? Okay. The spin texture also on this Fermi arc, you can calculate. It's something that comes out of the calculations, and you can relate it by symmetry again. Okay. Why do all this work? Well, because the system has interesting properties. It is superconducting. Those arcs turn out to be superconducting, and that's where I will get to now. So I'll get to the more experimental part. So you can compare, as you showed earlier, the bulk band structure to angle resolved photoemission experiments. These are the experimental data of our colleagues. So this is momentum in the Brillouin zone. This is energy. The intensity is actually the spectral weight, the spectral density they calculate, which in a single band system, in the non-interacting one electron approximation is equal to the band structure. And you see the different bands really matching up between theory and experiment. Also, if you do it at a different KZ, it's a longer story that in ARPES you measure the two-dimensional Brillouin zone. In principle, directly, if you want to know something about KZ, the momentum that's perpendicular to the surface you're measuring, you have to change the incoming energy of your photons. But believe me, if you fix Kz at another value, at 19 electron volt in this case, or corresponding to an energy of 19 electron volt for this system, again, you see a very nice connection between the band structure and the measured ARPES data. You can look at the Fermi surface, and also there, theory and experiment agree exceedingly well. Just to tell you, this is not an exception. This happens. This is I think, particularly a nice set of data, but of course there are more materials where you can find such very nice coincidence or agreement between theory and experiment. The Fermi arcs for the two terminations, they are also found in the experiment. They are sitting here. For the other termination, it's sitting here. It's very hard to see in those larger scale plots. But now, if you look at the cut of energy versus momentum, these are very bright spots, or actually they're small arcs. They're dispersing a little bit down, cutting the Fermi level here. These small arcs are very, very clearly visible at the place where they are also in the calculations. So now comes the big surprise. This system does not have any superconducting phase transition in the bulk. If you now look at ARPES, however, you see the following. So this is data, ARPES data, where is the difference between the data measured at 10K and 3K. Yeah. And what you see is that what happens is that for that difference, there's a shift. So red is where spectral weight goes down, is lost, and blue is where spectral weight piles up. So this is clearly the opening of a gap at the Fermi level, close to the Fermi level. And if you look a bit closer between the data, the ARPES data, so this is now intensity as a function of energy for a given momentum. You see that at 10K, this peak is there. It shifts a bit to lower energy and actually opens up a gap. So here also at another K point, a gap opens. And indeed, if we do our DFT calculation and introduce superconductivity, which we cannot introduce ab initio, or it's very difficult to do in general, and we didn't do it anyway. So what you can do is do a linearization of the bands and build a Bogoliubov de Gennes Hamiltonian. So you have the non-superconducting part given, and you add by hand a pairing between the electrons. And if you do that, you see that also there, as you expect, a gap opens up in the calculations. And by doing that comparison, you can see how much of a gap you need in order to explain the experimental data. Here's the data again. So now this is as a function of temperature, the energy of this gap on this. These are two different samples. You see there's a gap of about 1 milli-electron volt until you had hit an energy of 989 Kelvin. This other sample, you see that there's a gap that's closing when you reach 14, 15 Kelvin. So what our experimentalist friends say that there is a temperature at which this gap closes. It's different for the two. This critical temperature, it seems to be different from the two terminations. For the decorated honeycomb, it's 14 Kelvin. For the Kagome-like surface, the other surface, it's 8 Kelvin. Okay. Oh, yeah. One point I wanted to make is that there are also bulk-like features in the data, of course. But if you do the subtraction between 10 and 3 Kelvin, you see that those bulk features do not change much, or they do not change at all. So that really points at well, something's happening here maybe. But this spectral weight for the edge states changing really points at there being superconductivity at the surface. Okay, so we did a bunch of work on the centrosymmetric version of platinum bismuth 2, which is interesting because that is a bulk superconductor, and it's a bulk superconductor with a transition temperature of 2.5 Kelvin. Yeah. It turns out that if you do a measurement, it does not have superconductivity at the surface. So pressure or doping restores inversion symmetry, and it induces bulk superconductivity in platinum bismuth 2 with this temperature. What one sees is that if you do a transition to the centrosymmetric structure, so this is the coordinate of the Weyl points, the two Weyl points, and the two Weyl points, if you make the system more and more centrosymmetric, these Weyl points, they go towards each other until they annihilate for the centrosymmetric structure. In this path towards centrosymmetry, there are also other Weyl points that appear and then in the end disappear. And the Weyl nodes, they move in energy somewhat, but it's all very, very benign. We also wrote down a effective low energy model for platinum bismuth 2. That's a 4-band model that respects all the symmetries of the system. It has Weyl nodes and it has Fermi arcs. The way to write down such a model is, or the way we did it, is that we start with the Dirac cones, a system that has inversion symmetry, and we break this inversion symmetry by introducing a particular term, and then get the Fermi, the Weyl nodes going and the Fermi arcs going. So I don't want to talk too much about the model. It has some nice features. Well, of course, the 4-band model respects all the symmetries of the system. It produces the Weyl nodes and produces the Fermi arcs. So here you see the nodes as they are in the model, and the Fermi arcs that also appear connecting the Weyl nodes. If you look at the superconductor, there's something interesting you can do in the calculation with this model. Well, first you can say, okay, I take a slab of the system and I make it superconducting, introducing just some gap. And then here you see indeed the band structure becomes open and the gap forms. I could also introduce a pairing that's only at the surface. And then again, here you see, at least for the surface band structure, there is a gap opening up. And now I can build, if I want, a slab where I have superconductivity on one half of the slab and also on the other half, but there is a sign change between them. This is a pi junction with two superconducting surfaces. And if you have such a pi junction, it's known you will have a Majorana state. And that's an interesting aspect, we believe, of this material. So here is the calculation. If you have two superconductors in the model, at least, that where the left part has a plus sign in the face and the right part has a minus sign in the face, and then you can see that there is a mode appearing here, a zero mode, a zero energy mode, a Majorana mode. And if here is the position of that node, or the density of that node is plotted as a function of z, as a function of the coordinate. And you see that this node is in the center, right at this junction, if the distance between the left and right is 0. But if the distance becomes larger, if this gray part becomes larger, if the metallic part becomes larger, also the the width of the Majorana mode becomes larger. So the idea is if I would make a small flake, I would have superconductivity on the top, I would have superconductivity on the bottom, and between those two superconductors, if I make a pi junction, and there's a Majorana mode living there. Okay, so that was the story, or at least part of the story, until 3-4 weeks ago. And the new data shows the following. Actually, this data was taken by Srimanta, Chandni, and a group of Borisenko, Sergei Borisenko, in Dresden. So it's laser ARPES. It's a technique you can do in the lab. You don't need to go to a synchrotron for that, which is an advantage. A disadvantage is that with a laser, your incoming energy is not very high, so you cannot cover all of the Brillouin zone of this material. But it's enough. Srimanta showed that it's enough to find the arcs, and here you find them very, very clearly, the Fermi arcs in the two-dimensional Brillouin zone. If you look at momentum and energy, you see that, again, there's the dispersing arc, and here's cutting the Fermi level. The advantage of laser ARPES is that you have enormous control, and you can get very, very high quality data. And the high quality data, you can see from the quasi-particle peaks. So they're extremely quasi-particle peaks. If you cut at a given energy, so the Fermi energy in this case, across, and you look at the width of this peak here, it's here, that should be here actually. No, this should be here, yes. It's 2 milli-inverse angstrom. It's extremely sharp. If you cut in energy, the width of this peak in energy is 1.7 milli-electron volt. And my colleagues tell me that that's a record, actually. That's the sharpest peak in photon emission that they have observed, and they believed this to be true worldwide. Okay, so that very, very nice technique now allows you to look at this gap again and look at the momentum dependence of the superconducting gap. So here's the Fermi arc. It's plotted again in the two-dimensional Brillouin zone. And what Srimanta did is define an axis. So she said 0 degrees is here, and then 90 degrees if I rotate. This is 90 degrees. I rotate around this point here, and I can rotate back to 180. And what's plotted is the size of the gap. So you see that if the angle is like 90 degrees or going towards 180 degrees, the gap is sizable and large. It's about 2 milli-electron volt, if I remember well. But if you go towards the point where the node, or where the Fermi arc crosses the high symmetry line, and that's where the intensity of the arc is highest. If you go to that point, the gap is lowest, and you can see it in the data here. This is comparing the two temperatures for different angles. Here's the superconducting gap as a function of this angle theta, and you see that if theta is 0, so if you are here, the gap is statistically 0. And if you go up there, the gap goes up until you go to a point where you start losing the arc, the Fermi arc, and there the gap goes down again because the system becomes more and more bulk. The character of the Fermi arc becomes more and more bulk. So this really looks at like superconductivity. It looks like surface superconductivity. It looks like surface superconductivity with a node. So it's unconventional surface superconductivity. Okay, my conclusions and open questions. I showed you only a very small portion of the data. I didn't show you STM, if you're interested in STM and how they measure the superconductivity there. I'm happy to talk about it. These are the conclusions of this talk. The surface of trigonal platinum-bismuth 2 can be superconducting. Bulk states do not show a sign of superconductivity. The topological Fermi arcs carry a superconducting gap in this system. DFT calculations fit the normal state spectra. The empirical surface pairing using a Bogoliubov-de Gennes fit model fits with the ARPES data, and we also gave a 4-band model. The open questions are big ones, I would say. There's a lot to explore here. First question, is platinum-bismuth 2 an unconventional superconductor? The data of last month tell us yes. What is the origin of this surface superconductivity? Don't know. Relevance of the inversion symmetry and the topology for the superconductivity. It's definitely the Fermi arcs are superconducting. Those guys are superconducting, but is it essential that they are Fermi arcs? Is it essential that they are topological? Is it essential that they come from a Weyl node? Or are they just some surface states that are sitting there and happen to become superconducting? I mean, we have no insight in that yet. Can the topological zero modes, the Majorana modes, where the gap is 0 in the data of Srimanta, also that there is a Majorana mode. You saw a Majorana mode sitting there. The gap goes to 0 at 0 degrees. That's a Majorana. Can these Majorana modes be exploited in devices? And then did not talk about this. Does the large gap observed in STM, STS promise even higher TCs? This is my talk. Thank you for your attention.
We have time for questions, so Oscar, yeah. Do you have a mic?
That's a good question. So there are no surface states like that, and there's no superconductivity observed there. So the other surface states are bulk states that, say, bounce off the surface, right? They have because of the boundary conditions, they are somewhat different at the surface. But experimentally, nothing is seen to those states. These are also very dispersive states. So there are no local, the reason we see, you could also say, the reason we see something in the Fermi arcs is that they are so nicely localized. That makes whatever happens to them very clear. It could be that a similar thing is happening in those other states, but they are so completely delocalized that you don't notice. That is possible, but.
Other questions? Okay, on the back.
We use S-wave in the BGG. Yeah. So when we wrote the paper, the experimental theoretical paper published in Nature, we put S-wave pairing in there because what else would you do? And now with the new data, we see that there's a gap. We now looked at all the different pairing channels. These are now more complicated and interesting. But you can classify all that. But then to build a Bogoliubov-de Gennes Hamiltonian for that is quite challenging. Actually, we are trying this, but because it's not S-wave, you get many more possibilities, and it's hard to do something that you can trust halfway.
Question, yeah.
Can you hear me? I have a clarification question about chirality because that's very central to a lot of these phenomena. So an edge current is like a loop of current, right? An edge state. A flat loop of current is not chiral, right? Like a single spin is not chiral. So in what sense is that a chiral edge current?
Oh yeah, to be chiral, you need 3 dimensions, right? In 2 dimensions, there's no chirality. That's absolutely true. So these nodes, they actually are 3-dimensional objects. So there is a chirality in the sense that, in the precise sense, that if I take one node in order to one certain chirality, in order to produce a node of another chirality, the operation that I have to do is mirror. Without a mirror, I will not be able to match the wave functions. So and it's a 3-dimensional system, so that guarantees, I would say, chirality. I've broken inversion.
So you're saying it lacks mirror and inversion
yes.
in 3 dimensions, and they cannot be overlapped,
exactly,
made congruent with each other.
So that is a good definition for the Weyl nodes. So the chirality, I'm not sure if I said chirality, if I talked about the Chern insulators. If I said it, I shouldn't have, because that's as you point out, another point.
So if you have Dirac cone in the bulk, you said invergent symmetry would give you Weyl nodes, right? But if every surface breaks inversion symmetry, so every Dirac cone material on the surface must be a Weyl?
Okay, so to have a Weyl node, which are properties of the bulk, of a bulk band structure, you need either a broken inversion symmetry in the system, if you have time reversal respected, which we have here, or the other way around, you have to, or both, time reversal and inversion need to be broken. But this is really bulk inversion symmetry. If you go to surfaces, you also break inversion, but that will, in general, if you have a system that is inversion invariant, and now you look at the surface and you say, I break inversion there. There are different ways to break inversion. That's an interesting topic in itself, how you break inversion at surfaces. You can break inversion definitely from the bulk to the non-bulk or to the vacuum, but also you can break inversions in the system. But in general, that I don't know of any example where that gives you anything like a Weyl node.
It does not.
It does not.
Okay, thank you.
Actually, I had a quick question. So is there anything interesting with transport data? You didn't mention transport data in the...
Yeah, so there is transport data. Yeah, so the problem of transport is that if it's really a layer or a couple of layers that are superconducting in there, how do you pick up the conductivity of those layers experimentally? So there is STM here, where they see very nicely the atomic structure of the 2 types of surfaces. And here you see the superconducting gap as it should be seen in STM, but it's huge. It's 10 millielectron volt. It's not everywhere they find such a large gap, but we don't know why. The gap closes in field, all fine. Mystery. Now here's another one, which I really like, because it's a very simple and technique and gives you a very nice result. So it's point contact spectroscopy. Basically, you drill a needle into your system, and you look at the conductivity, and the tip induces a superconductivity. You see a superconductivity if you drill the tip in by this point contact spectroscopy. And now it depends on what kind of tip you use, but it's between 3 and 8 Kelvin. So that is a probe of superconductivity, but not the one, not a four-terminal measurement of resistivity. Interestingly, there is a bunch of other systems, but except for platinum bismuth 2, where if you do point contact spectroscopy, you find superconductivity in there. So it might be that there's something more general to systems having topological surface states being superconducting, but more question marks than answers.
Any other questions? Okay, Oscar, maybe one last question.
Two. So I said you get regions. You get regions with very large gaps, like this one. Yes. So now there is also Bena-Kalinski did squid data. So where you look at the actually the response, the diamagnetic response at the surface, and indeed, so I will not show you the data, but what I understood from her experiments is that indeed there is a Meissner a diamagnetic response from the surface, which you associate to superconductivity, but it's also clear from that data that it is very inhomogeneous. So some portions of the surface have a large response, some portions have a much smaller response. And in itself, I would say what we know now, I was very puzzled by that a few months ago. Now one can say, well, what do we have? We have a system that is superconducting at the surface. This is already something fragile. And now this thing that is superconducting at the surface also has nodes. So this becomes fragile squared. So if I have now, my surface has some kind of defects, impurities, rows of atoms missing, whatever, certainly this will have a large effect on the superconductivity. I mean, we just, it's essential to get good surfaces of this system and to get really good experiments on those better surfaces.
All right, so let's, oh, you had a question? Oh.
In such systems, I mean, if the surface is superconducting, but the bulk is non-superconducting or whatever, metallic insulating, wouldn't a four-probe contact give you a resistive drop? Or if there are bulk supercurrents generated, magnetization should give you a drop in susceptibility or something?
Yeah. So you're saying also if something happens at the surface,
right.
It should, yes. Okay, so now I'm the theorist, but I can understand my experimental colleagues when they say, I'm looking at 10 to the 19 layers, and you're telling me 2 of those layers become superconducting, and now I have to tease that 2 layers out of my data, out of the 10 to the 9 that are just metallic. That's a problem for me. I
mean, the current profile, whatever, is flowing from one contact to the other contact via a few layers. If it is...
Okay, it would be fantastic if people would be doing it. I guess the main problem is to get the contacts up there and to get contacts there that probe as much as you can the first bunch of layers. And then what I said before, by now we know that there is superconductivity there. The gaps measured by ARPES are average gaps over the system, over some region, the size of that they probe. So there is much more. So even if you would get those macroscopic contacts there, perhaps there is not a percolative path between the superconducting states. I would not even guarantee that. Mm-hmm. So it's really something tricky, I guess.
All right. So let's thank Jeroen for a very nice and interesting talk.